Alright, so today I wanted to do a quick review of data structures and how we do proofs and recurrences. Okay, so I don't think I'll get to recurrences actually. I had a bit more ambitious when I started making this slide. So we'll get a sense of some basic data structures and we'll try to do some proofs. Alright, so and this is in general part of the first few lectures of this class will be a bit of background. So we'll be going somewhat faster than normal. So if you feel it's too fast, just let me know if it's slow down. Okay. So today we'll talk about data structures and I'll also give some examples of how you show correctness of algorithms. So, alright, so what are data structures? So how many of you have not taken a data structures class? Actually, how many of you have taken maybe like more than 2-3 years ago? Okay, so it's good to do a short recap, I guess. Okay, so what are data structures? So recall that we said we defined an algorithm to be something, some procedure that converts an input to an output. Right? So that's how we define an algorithm. And so one question arises, so how is the input actually stored? And that's essentially what data structures are about. It's about how you actually represent the data that you have. So you might wonder, is there a difference between one way of representing data and the other? And we'll see that in many cases, having the data stored in the right way could actually lead to much more efficient algorithms. In fact, we saw an example of this last time. So can you guys, anyone want to say how we saw an example of this last time? Yeah.
Binary search tree. I mean, you could represent it in an array or in like a binary tree, but...
Yeah, so last time we saw that if you had a sorted array, then you could actually do querying really quickly. Right? So, and if you had an array that was not sorted, then it would take like n steps, while if it was sorted, it would only take log n. So that's an example of how you stored the data. Right? So you could call it pre-processing, but that's essentially what happened. And now if you had multiple queries, you could do them all really quickly. So that's what I mean by representation. Okay, and that was a particularly simple one. Okay, so I just thought I would give a few examples to give you guys a sense of the kind of data structures we will use. So most of this class we'll be using very simple data structures. So and this is more of an example to illustrate what kind of things exist. Okay. So the first example is what I call the Scrabble problem. Okay, so it's somebody puts a word, you want to know if it's a valid word or not. Right? So you have a huge dictionary and given a particular word, you're supposed to find out if it exists in the dictionary or not. Okay. And usually in these problems you assume that the dictionary is kind of given, you can do some pre-processing with it, and then you have multiple queries. And that's typically the use case scenario. Okay, so how should one store words here? Yeah, so you could have alphabetical. I heard hash somewhere. That's also perfectly fine.
A trie maybe.
Okay, so who said try? Oh, okay, good. Yeah, so we will actually drive that. So this is, you could also call it a prefix tree. Okay, so it turns out all these are perfectly fine ways of writing. By the way, does this look a bit, does it look too smooth for you guys? It's not crisp enough, right?
The display or the list?
Sorry?
I asked about the display or the content of the list.
Yeah, I don't think it's not blurred here, so maybe the display. So, but everyone can read what I'm writing. Right? Great. Alright, so it turns out all of these things are pretty reasonable, at least for this kind of a simple problem. Right? So if you just had a dictionary of a few thousand words or maybe like 20k words, this is perfectly fine. Either of these will work fairly well. Okay. So if you had alphabetical, then what would you do?
Binary.
Yeah, you do essentially binary search, right? Alphabetical is the same as saying it's sorted, so you could do binary search of sort. So it turns out for text, this last, the prefix tree or a trie is probably the best kind of way of writing things. Okay, so I'll just describe briefly what it is, and you will see how you can very quickly do things. Okay, and this will also give an example of what we look for when we say, when we talk about data structures. Okay, so that's kind of the point I want to make, and this is just an example. Okay, so what are tries or prefix trees? Okay, so it's a data structure. So it stores a collection of strings. Right, so this is a structure that stores a collection of strings. And what might you want to do with this? Okay, so one example is you might want to add or remove a word, and this should be doable pretty quickly. Right, so if you have a new word you want to add to the dictionary, you should be able to do it quickly. Okay, so this doable easily. Okay, so in the examples you guys gave me, I think alphabetical is also pretty easy unless you store it like a list or something, in which case insertion could be a problem. Okay, so you can quickly find where to insert, but yeah. Okay. So you can think about these kind of things. Okay, and also we want to look up a word. Okay, so this is probably the operation we want to be the fastest, right? Because we have a fixed dictionary and we want to make multiple queries to it. Okay, so this is something you want really fast. And you might like to do other things, like you might like to do counting prefixes. That is, if I give you, like a dictionary could have multiple words, so it could have a word that says allied or something, and now I give you a smaller string, ALL, and ask you how many words actually start with ALL. That's something reasonable that you might want to do. Okay, and these kind of, actually I gave a simple example for dictionary, but these kind of problems appear all the time, like in text search, or in genomics, like if you're searching through DNA strings and so on. Okay. So these kind of problems are very common, these string problems. Okay. So you can have problems like counting prefixes, and you can have various other operations that you might want to support. Okay. The point I want to make is that typically in data structures, you build a structure to store a bunch of items, and you want to support a few operations. Okay. So that's the goal typically in data structures, and in this case maybe these are the operations we want to do. And for strings it turns out, so it turns out what I call these prefix trees work really well, and the way these work is the following. So you have a collection of words, so let's say I have something like okay, this is probably not a word, but it's there, and you have ally. You know the usual, right? So let's have this 3 words. Okay, and the way you store this collection is in a natural way. So you first have a root node. So you store this as a tree. Okay. So it's stored as a tree. So there is a root node. This stands for the empty string. And you have a collection of nodes. So now for every letter in the alphabet, you have a subtree. Okay, so this is for A, this is for B, C, and so on. Okay. And you have a node here. And you have a node for each of these things. Okay. And similarly, you have things out here. All right. And so in this case, I won't, since I don't have any words starting with a B, I won't have this subtree. Okay, so this tree stops here, and it says that this is not a word. Okay, so at every vertex, I also maintain a boolean, which is supposed to denote if the string until that point is a word or not. Okay, so I'll get to that in a bit, but so just notice now that since there's no word starting with a B, I just have an empty dangling point. And I have words starting with an A, so I have here, and here I have these things. I have one for D and one for L. And here I have these and I have again for A and so on. Okay, so this is how I want to store these things. Okay, and here, so is the construction of this tree clear? For every word, I try to trace a path from the root to and basically spell out the word. Okay, so there's a pointer at every point. So if I want to spell out now cat, then I start at the root, I do C, and I go to a pointer which is named A, and from this node I will have a pointer for T, and I go. And any word that doesn't exist, the corresponding pointers could just be empty. Okay, so for instance, there is no C, D something, right? So this points to an empty word. So this is how you build the status structure. Okay, so again, the details of this are not terribly important, but you should get a sense of how I'm doing this. Okay, so any questions on how I'm doing this? Yeah.
If you need to find if a word exists.
Yeah.
So we sort of move through this tree.
Yes. So I haven't told you how I indicate the end of a word. So for every node, there's also a Boolean yes or no. So for instance, if I look at this node, so I look to see if AL is a word or not. Okay, and AL is not in my dictionary. Okay, so I write down 0 here. And ADAM is a word in my dictionary. So here I put a 1. Okay, but everywhere else I have 0. Okay, because they are not words in my dictionary. Okay, so every node has one Boolean, which is supposed to determine if the word so far is in the dictionary or not. Yeah.
From every node, will there be till 26 characters?
Yeah, so technically yes, so you have pointers, but since there are no words here, they would just be pointing to none.
Like from A we took out D and N only, but actually
Yes.
there will be A, B, C, D till Z.
Correct. Any pointer that I have not written, you should assume is pointing to null. Okay, so the pointer will exist, but it will point to null. Okay. So that's how yeah. Okay, so these will be pointing to null. Okay, so the same with the root, and this points to null.
Yeah. Does it mean that then every node has a letter and a Boolean digit stored in them?
Every node, every edge has a letter, right? So that's essentially how we are thinking. So yeah, but when you implement it, you will implement it as you have a node, and every node has 26 pointers. Some of them could be null, and it will also have a Boolean. Yeah.
Is it infinite?
No. So I mean, because most of the things will be null, right? So it won't be. Right, so you won't have edges out of a null. Yeah.
So in practice, like for predictive text, they usually set it up where it's most frequently used first to
Yes.
search, or?
So, right. So what he's asking is, suppose your dictionary had, had in some sense some bias towards letters, then maybe you can build a smarter tree. Is that what you're saying? Yeah. So you could do that. There are ways of doing that.
Like real important, there's certain letters you guess first, right? Because it's most frequently occurring or something like that.
Right, or you could have pairs of things that appear so commonly that you might want to treat it as a new letter by itself or something. Then your query time could reduce. So very often in practice you might, if you have commonly occurring patterns, you might want to have treat that as a new letter. Okay, so and that might actually save you space and so on. So let's not get into that, but this is the simplest form of a trie. So, alright, so now if I want to add a word, how would you do this? Yeah, so you just go down the tree, right? So suppose I want to add dog, then I start in the root, I see the pointer to D is null. So I now create a new node which is D, and then I create a new thing which is for O and G. Okay, and I set the Boolean variables here to be 0 and the last one to be 1. So some of this tree may have existed, in which case I'll only add what I need to add. Okay. So that's so this is how you add. So how long does it take to add a word of length L? It takes O of L steps, right? Because you have to do some Boolean assignments. Okay, so what you can see is that adding a word, even removing a word is very similar, because you just, actually this is just constant time, because just oh no, actually maybe you have to traverse the tree, so you need L time, then you flip the bit to 0. Yeah.
So if you wanted to then insert dogs, or would there be a 1 on the G?
Oh yeah, it's a good question. So there will be a 1 over here, and there will be a pointer S over here with a new node, and this will have a 1 also. Okay, so this is how we support multiples.
So like do will also have like, because it also spells do.
Yes, do is also fine. So if this was also in your dictionary, then this would also have a 1. Yes. So, it's good. Yeah.
So what if I want to remove one of these? I mean, if I have do and dog and I want to remove dog,
Yeah.
it will remove do as well?
No. So that's the thing. So that's what I was saying. So if you want to just remove dog now, this is a good question. So if you have do, dog and dogs also, what you need to do is just set this bit to 0. Okay, now you make no changes to the tree. Okay. So there could be situations in which you actually make changes to the tree, where if this was a leaf node, you might want to, suppose I want to keep dog and remove dogs, right? So then what I do is I just set this to 0 and I notice that there's no pointers out of this. Okay? So I could actually remove this if I want. Now, you need not do this, you can keep it around, but it's a waste of space. Okay, so any other questions? So hopefully the data structure is clear now. Okay, so once you have this, looking up is also trivial. What about counting prefixes? Yeah.
If you also keep an image at each node, you can do this in the same time, without increasing the flexibility.
Right. So what he's suggesting is that instead of just a Boolean at every node, it says if it's a word or not, have a count of how many things are in the subtree. Okay. So you can have a count of how many words are in this subtree, for example. Okay. Now this is a common thing people do in data structures, which is storing additional stuff inside nodes. Then you've got to be a bit careful. Okay, so for instance, you've got to make sure that when you're doing these other operations, you actually maintain consistency. Okay, so now your implementation for adding a word actually changes, right? Because you go down, add stuff, and then you go back up the tree, and you have to increment the count of everything by 1. Okay, so your addition time will now be doubled because you have to go down and then go back up. Okay, but that's fine.
Couldn't you add it on your way
You can
down?
add on your way too, yeah. But it's one extra step you need. Yeah. So, okay, so any other? So everyone see the point I'm trying to make. So usually it's a good idea to maintain additional stuff in data structures, but you have to be careful about how you update them. Okay. And there's there are more complicated data structures like balanced binary trees and so on, where you can store additional information at nodes, but then you have got to be careful. Like if I do rebalancing of the tree, can I actually maintain these quantities? Things like this. Okay, so so I don't have space in the homework to add a problem like this, but you can think about things like this. So, alright, so this is just some basic introduction to a string data structure that I wanted to give. So this is an example of how typically data structures would look. Okay, and so what you've got to know when you're talking about a data structure is what's the kind of data it stores. Okay, so in this case there were strings. Okay, sometimes there could be integers, sometimes it could be vectors and whatever. Okay, so that's the first question you should ask. Then you should ask what the operations are. Okay. So very often you have some add, remove type operations, but you could also have more complicated ones. Okay. So for strings, we just saw that you have prefixes. You could have some substring type queries that you might want to have and so on. Okay. So you've got to ask what operations are supported, and you're interested in the runtimes for the different operations. Okay. So these are what you should look for when you talk of a data structure. And also, maybe we will see one example of this, but you might want to see what operations you use more frequently when you're actually talking about runtimes. Okay. So we'll see an example where binary search trees have pretty good properties. They have log n time for everything, for all the operations we want to support, but there are some situations in which you do one kind of operations really often. Okay, so then maybe you want to speed up that single operation and maybe slow down other things. Okay, so there's a lot of trade-offs here. Okay, so that's why I have runtime for different operations. They could be different. So the other point I wanted to make is that very often when we talk of runtime, we talk about worst case, which is, for instance, in the string example, right? So any string of length w could be added in this much time, right? So there's nothing special about it, right? But often in data structures, you also talk about amortized running time. Okay, so anyone know what amortized means? So has anyone seen? Yeah.
Situations in which the algorithm will run fastest, or it's like when it's in a prime state, like binary tree when it's fully balanced, it will be an amortized binary tree.
Yeah, that's one example, right? But in general, the English word amortized means averaged over time. Okay, so yeah.
How does this go to data structure?
Yeah, so amortized is in some sense the average over a bunch of things, okay, and that's literally something that you might care about in some application. Okay, so for instance, you might be building a dictionary, and in the building phase, all you're doing is adding, right? So you're adding a whole sequence of things. Okay, so what amortized running time means is that you do a whole bunch of operations in one shot, I mean one after the other, and you see what is the average time it takes to add one element. So it might seem surprising how it could be better than adding each one separately, but you could actually get a better bound for amortized analysis typically. Okay, so it's the average time of an operation. Okay, so here an example could be adding a new element or something. So what you should think of is if I add a whole bunch of elements, I add some n elements, and that will take a certain amount of time. That divided by n is the amortized time. Okay, so any questions on this? There's just a notion that I wanted to introduce so that you guys are aware of, we won't really be encountering amortized analysis in this course. Okay, so the other thing that I wanted to mention is, so this is another very basic data structure that you should all be aware of. Okay, so this is binary search tree. Hopefully, how many of you have seen some form or the other of this? So if not, you should go back and read some of the notes that I've pointed to on the course page. Okay, so this is very fundamental data structure. And it's used for storing integers. Okay, and it doesn't have to be integers, but any set of items where you can actually compare any two items. Okay, so these are like any totally ordered set. So you can store any set of objects where between any two you have a comparison. Okay, any two are either less or bigger. Okay, And this is a very good general purpose data structure. Okay, so if you this also the standard template library for C++, it has a set operator which basically implements a binary search. So what does a binary search tree do? So you have so the operations it supports. So remember, when we talk of data structures, you've got to ask yourself, what does it store? I already said it stores integers. Then what does it do? It supports adding and remove elements. You can query if an element exists or not. You could also find the max element, find the minimum. Okay. So this is what a binary search tree does. And all these operations have a worst case log n time. Okay. So that's yeah, so how would you implement a binary search tree? I'm not going to go into the implementation, but how would one implement it? Sorry?
Adjacencies.
How?
So, I mean, different types of binary search trees. So maybe you could have a root node, and if you get some number, suppose if it is lesser than that, then you put it in the left subtree, or if it's greater than that, and put it in the right subtree. So ordering and something.
Okay, so what you're saying is, if I have a bunch of elements, I add them one after the other, then you start with one element at the root, and you add elements in order. Okay, so I get a bunch of elements A1, A2 up to AN. Okay. Then you add A1, and then you put A1 here. A2, if it's less than A1, you add it here, and so on. Okay, and yeah, so this is fine, but this could in general be bad, right? So yeah.
Be an array where the first entry is the root, the second two are the left and right trees.
Yes, so that's also fine. So that's yeah, that's another way of storing this. But there's one problem with both of these. So, yeah.
Double linked list?
So what do you mean by that?
Like a linked list with two nodes which are pointing to the left side or the right side.
Yeah, so you just mean write them out as A1, A2. Oh, sorry. To AN, and you just have the next and the previous. Yeah. But now how do you, for example, query if an element is in the list or not?
I didn't mean previous, like the left or the right.
Ah, okay, it's like it's still a tree, but you want a left and right.
We need to balance the tree.
Balance.
Yeah, so if you just add elements like you guys have been describing, one issue will be that depending on the relative magnitudes of these A1 through AN, okay, you could have a tree that's extremely lopsided. Okay, so for instance, if like in this example, if I had A1 less than A2 less than so on, less than AN, so this is a really nice collection, right? It's happily sorted. But if you try to build a tree like this, you would just go to A1, you would build A1 and keep adding things to the right. Okay, so you just do A2, so on. This is an extremely unbalanced tree. Right? There's nothing to the left. Okay, so it turns out there's multiple ways of doing this. So and typically, when you're adding, occasionally you need to rebalance it. Okay, so there's a bunch of ways of doing this. So it's like tree building plus rebalancing. Also, all the answers that you said with respect to building a tree are perfectly fine. You could have arrows in both directions, you could have things stored as a list with the first element being the root and so on. So these are all perfectly fine. Okay, so this, as I said, every operation is log n, so it's relatively fast. Even for pretty big n, this is good. But there are some applications in which you may want to do some of these faster. Okay, so in particular, we'll see an example of constructing spanning trees where you typically want to find one element which is the max and keep removing it and things like this. Okay, so does anyone know of ways that could help? Yeah.
So using the heap.
Yeah, so there are other structures that build off this. Okay, so they're not that crucial, but it's good to know that. So this is what I was saying earlier, that typically you use data structures inside a particular algorithm, right? So now that algorithm could be always inserting or always trying to find a max element or always trying to find a min element. Okay? In which case you observe that, okay, instead of using this general purpose data structure, maybe I should come up with one where, say, the max, finding the max is very optimized. That's exactly what a heap does. Okay, so yeah.
From the roots of the tree and then to find the vertex of the tree and reach the maximum.
Yes, that is true. I mean, but that will take log n time to find because you go down the tree, right? So what a heap does, a heap is a slightly different data structure. We won't go into this, but that actually stores the largest element at the root, okay, and it keeps another binary tree with a similar property on both sides. And you can also do searching and stuff. Yeah. So let's not go into that, but this is a another well-known data structure. Okay. All right. But the point I want to make is that depending on the algorithm in which you are using this data structure, you may want to come up with a smarter structure itself. Yeah. And you could also ask yourself, suppose I want to find the kth smallest element. Can I do it using a binary search tree? So, does anyone know how to do this? So it builds off what you were suggesting some time ago. Yeah. So that's the hint. So you want to find the kth smallest element. I give you k.
Need to store how many elements are there in each subtree.
Yeah, so it turns out you can do the same thing as we did with tries. Okay, so you can actually store how many elements are there in each subtree, and maintaining these counts when you rebalance is somewhat tricky, but it's possible. Okay, so that's the bottom line. Okay, so it's you can do operations like this also pretty quickly. Okay, so all right, but broadly, what you should remember is that this is a great data structure. It's typically, it works, it's like a thing that if you don't know what to try, you just store things as a binary search tree. Everything works reasonably fast. Alright, so that's, this is for storing numbers. Right? So how do we store graphs? Okay, so a graph is basically you have a bunch of vertices, you have a bunch of edges. Something like this. And for now I'm thinking of an undirected graph, so you don't see arrows on the edges. Okay, so this is an undirected graph. I'll always write graphs as v comma e, where v is the set of vertices and e is the set of edges. Okay, so this is how I have store a graph. I mean, this is what I mean by a graph. So how do we store a graph, right? So again, we can store it as v and e, right? So just what the set of vertices is and what the set of edges is. Every edge is just a pair, so it's like a unordered pair. So it's like u and v. And I could just store a collection of edges, right? So this is a perfectly legitimate way of storing a graph. Okay. But what do we want to do with graphs typically, right? So we might want to say, we might want to find a list of neighbors, or we might want to see if two nodes u and v are connected. Okay, so we want to see if an edge uv is present. Right, so we'd like to have data structures where these kind of operations are easy to check. Okay. So again, so all of you answered this last time. So how would we store things so that a list of neighbors is easy to find? Yeah, just store the list of neighbors, right? So for every vertex, you store the list of neighbors. Okay, so you just say that A of U is an array containing all neighbors of U. Okay, so this is how you store. This is what's called the adjacency list. And so, how long does it take to see if two nodes U and V are connected? Like if I give you U and V, and I ask you to see if U and V have an edge. Yeah, so you will go through this array and you will see if U is there in the array or not, right? Oh, sorry, you'll go through the array for U and see if V is there in the array or not. Okay, and so could you do this faster? This could, if U has a large degree, this could take a lot of time, right? This could take over time. Okay, so the query takes O of degree of U time, which is sometimes not so good. So another way to store it is you could store a matrix. Okay, so you could have a matrix that says A of okay, I'm going to write it like we do in math. And, okay, so A of UV, it's a matrix which is 0 or 1. 0 if no edge, 1 if there's an edge. Now this has its own set of problems. So any
It takes up a lot of space if it's a square.
yeah, so I mean you can never do such a thing with like the Facebook graph, right? So this will never fit in memory. So this is n squared space. Okay, so this is something I didn't talk about, but data structures in particular, you've got to be very careful about how much space you're using. Okay, so this having more space might offer you faster query complexity, but you might not be able to actually store this. Okay, so this is what people call time-space trade-offs in data structures. Okay, so and that's a big area of research in itself. But so this is a very simple case in which this happens. Yeah.
In the previous case, what did you mean by degree of U?
Oh, so right. So this is a basic notion. So a degree of a vertex is just the number of edges that U belongs to. Okay, so degree is adjacent to a vertex. Okay, and adjacent means number of edges that U is a part of. So again, so it means that you have not done homework 0. But anyway, yeah. So, all right. So this is the thing. So anyway, you can avoid degree of U. So degree of U could be as large as n, right? Because a vertex could be connected to everything else. Okay. So given what we know, what could you do? Yeah.
You also use a CSR array.
What's the CSR?
The CSR array is where you store your connection vertices and your counts in 3 separate ones, and it makes finding paths and connections very quickly. It's only like 2 or 3 steps.
Okay, that could well be, but I don't know about it. So we can talk about it later. But given what you've seen earlier, so can you?
Yeah, you can assign numerical values to the nodes and then sort them. And they have log of degree n.
Yeah. So we've already seen how to store a collection of things so that query is fast. Right. So we've already seen that. So A of U is essentially. Here we are storing it as an array which consists of all the neighbors. But if we just had a sorted array, or if we had a binary search tree for every U, then you can just in log n time check if it's adjacent or not. Okay? So this is typically what people do if so people have like a small sorted arrays for every node, and you can quickly check if it's present. Yeah.
But for the binary search tree, we saw that it had to be totally ordered.
Oh yes, so I am implicitly assuming that because I am referring to A of U and so on. So I am implicitly assuming that every vertex has an index and it has its unique index. Okay. So again, this is something that I mean, so you can always put an order on things by first assuming that you hash it to a number, and then it's a number, so it's an order. Okay, so this is actually, I don't know if you guys saw. So on the course page, I had a link to this paper of Andy Yao. Did any of you look at it? Okay, so actually this brings me to one thing. So the course page on Canvas, it will have links to things like videos and some lecture notes and things like this. And it will also have additional readings. So please take a look at it after, maybe a day after class. And usually it will have something that you could do to follow up on what we did in the lecture. Okay, so last time I had a link to a paper which essentially says something like this, that you could always hash things to integers, and then it becomes a searching problem, and then the search problem becomes easier. So anyway, so that's one thing I wanted to say. So you can do all these operations in O of log n time. And so what's the space used for an adjacency matrix? No, not an adjacency, for the adjacency list. Yeah, so it's just number of vertices plus number of edges, right? Because for every vertex you have something, so you have at least constant space, and it's the sum of the degrees, which is basically the size. I mean the number of edges. Okay, so the space is O of size. Okay. And this is essentially best possible, because even if you just store the list of edges, take E. Is there a question?
What did you write O log n for?
Oh, this is for querying if U and V are connected.
If you use the adjacency matrix.
If you use an adjacency matrix, it's actually constant, because you can just check if AUV is 0 or 1. But if you use an adjacency list, but the list is sorted, then querying would take log n time, because you look at U's neighbors.
So space is number of edges or number of vertices plus edges, the space complexity?
Sorry. Yeah, it should be number of vertices plus number of edges. So yeah, very often E is the dominating term, so I just forgot that. Because you still have to have something for every vertex, right? You've got to say it's not connected. Okay, so alright. So maybe should we take like a couple of minutes break so that people are refreshed, and then we can. After this, I just wanted to quickly recap and then go into some proving correctness. So I want people to be more refreshed. So let's break for a couple of minutes and drink water.
In the previous slide, you said n square space for the first one. So how is that? N square space
for adjacency matrix
for the list of neighbors.
No. So, yeah, so I was saying that if you had a matrix AUV where you store zeros, then you have for every pair. Yeah.
So how is n square space?
Because for every U and V you have 0 or 1. So you have a bit for every pair. Yeah. is an array from
ग्राफिक्स में काम करो तो बहुत बड़ा बड़ा
哦，你那个是知道老师的，我懂了。我知道你中途这个顺序，并不是，对，并不是对，你这是建立的方式，你是用来哪种方式建立的，都是要把这个建如果是你来说二乘数的话，如果是二到四的话，它的大小附节点可能比两个附节点大，我一会儿看，反正就是所以说最顶端的，你在二乘数的来说。
Gary, got the H right, and I'm Terry. Yeah. Not a problem, I've only got one letter right. Yeah.
Oh,
I'm in machine learning before this and databases right after.
也就是说，你理解的这个二乘数的话，它其实没有什么顺序，就是什么是
That's kind of nice.
Alright,
So this one, I think this one about the big data math.
so let's continue.
Same with machine learning, that's why they're so big. Because they have lots of
Alright, so the next thing what I want to do is talk about how we will actually discuss algorithms. So we'll not just describe algorithms and analyze running time, but we'll also actually try to prove that the given algorithm actually finds the right solution. Okay, so this is something that at least throughout this course we will focus on doing this, okay, because we want to be sure that we have an algorithm that does something useful. Okay, and this is extremely useful to do for any algorithm. Okay, so this is correctness. Okay, so I wanted to go back, I wanted to give you guys a sense of how you formally write correctness proof for an algorithm. Okay, and I wanted to run through some examples because maybe it's not clear to everybody. Okay, so if you've taken discrete math classes in the recent past, this will be very easy, but bear through it. Okay, so alright, so let's look at a very simple example. Okay, so this is something we saw last class. So this is bubble sort, as most of you noticed. Okay, so what it does is you have an array A, and the thing is, as long as A is not sorted, you do this step. Right? So you just you have A1, A2 through AN. Go from left to right and swap the adjacent ones if you see that these two are out of order, if they are out of order. Okay, so maybe if A2 is bigger than A3, swap A2 and A3. So this will do some local corrections, and you do it from left to right. And keep doing this as until A is actually sorted. So let's try to see. So firstly, does this algorithm always result? Does this? In a sorted array. Okay, so this is the question we want to ask when we say that, when we want to prove correctness. Okay, so you've got to prove formally that whenever this algorithm, after this algorithm is done, it returns a sorted array. This in this case is trivial, right? Because the loop runs as long as it's not sorted. Okay, so the way I have written it, it is true. And is that clear? So the loop runs as long as it's not certain. So then the question is, does the algorithm always end? Okay, so that's equivalent to asking this question. Okay, so does the algorithm always end? Okay, and so this is an example where this sometimes happens, where the correctness proof and the running time analysis are kind of linked with each other. Okay, and this happens in many situations. And in this case, if you write the algorithm like this tends to happen. So, all right. So now, how would you argue that the algorithm will always end? So the claim that you've got to write down is the algorithm always ends in a finite number of steps. Okay, and you might want to show something stronger, like you might want to actually give a bound. Okay, so you maybe want to say that after n iterations of the loop, or something. So at most n iterations. So, yeah, n is just something I came up with, but if you want, you could prove something. Alright, so this is the first thing you've got to do when you're trying to show correctness. Okay, so you've got to write a statement that your conjecture is true and actually try to prove it. So stating what you want to prove is the first thing that you need to do when you're trying to prove something. Okay. So it might sound obvious, but people, unless you go about it systematically, it could be. Okay, so this is what we want to claim. Right? So how do we prove this? So this is the algorithm. You want to claim that the procedure stops after at most n iterations of this loop. So who wants to take a shot? Maybe someone, I'll come to you at the end. Yeah.
So after the ith step, the ith maximum elements always gets deposited at the end.
Okay, so you are coming up with a different claim, right? So you're saying that so you're making an observation that after I iterations of the loop, okay, so what happens?
The ith maximum.
Okay, ith largest element. Yeah?
Is like deposited at the end.
Is at its correct position.
Is at its correct position.
Okay. So do you want to say anything about elements, not the ith largest, but let's say the largest and I minus 1th largest and so on?
N minus 1 that largest, I think.
So what? I just want to demonstrate the kind of mild imperfections that people usually write. So that's why I was just trying to pick apart the thing and get the statement exactly correct. Okay, so that's what I'm trying to do. So I'm playing devil's advocate. Okay. So what you're saying is that after I iterations, the ith largest guy. So if I will be in its correct position, right? So you're saying. Let's call it A sub Ni. Okay. So N1, N2, so on is the sorted order. And A sub Ni is the ith largest. And you're saying that this guy is in its right position, so it's I from here, from the end. Okay. So do you also want to say something about the bigger guys? Because okay, fine, so maybe you prove this statement, but then, okay, so all you said is that after n iterations, the smallest element is in the front. Right? You have not said something about things that came afterwards. Do you see what I'm saying?
So I runs from 1 to n.
Sure. So after the first iteration, you said that the largest element is here. After the second element, you're saying that the second largest element is here. Okay. After the third iteration, you're saying the third one is here, but what about these other two? Maybe they got swapped.
Oh.
Yeah. So you've got to say that that doesn't happen, right? To be formally correct.
There's a term for that.
Yeah. So all you've got to say is that the ith largest onwards are correct, are in their right position. Okay. And so I'm just trying to point out that you've got to have the statement precisely right before you actually prove. Okay, so this is this is a very good starting point. So after I iterations, ith largest element onwards are at their correct position. Okay, so this is what you want to claim. And how do you prove this claim? Yeah.
You do it inductively.
Yeah, so one easy way to do it is proof, you can prove the observation by induction. Okay, so proof by induction. Okay, so, and how would you show it inductively?
So you would
Sorry? Well, no. Anybody is fine. Yeah. So if you want to, you can answer. If you don't want to, you can just. Okay. So yeah.
So I have a different proof of trees.
Oh yeah. Go ahead.
There are only finitely many pairs per iteration. At least one pair will be swapped, and each pair can only be swapped once.
Yes. Unfortunately, this gives a bound of n cubed.
Yeah.
So, but yeah, this is slightly better. So let's do this. Yeah. Okay. So how do you prove this observation? Yeah.
So you assume you take a case where the subarray is sorted for I elements and simulate it for I plus 1 element, and if the condition still holds, if the subarray for I plus 1 is still sorted, then it is proved by induction.
Okay, so this is how one proves things by induction, right? So you first do something. So don't you have to prove a base case first?
Yeah.
Yeah. So first show this for I equals 1 or something. Show for I equals 1, and then you've got to say, assuming the first I iterations work out correctly, I plus 1th iteration also satisfies this observation. So assuming ith iteration satisfies, let's call this observation 1. Okay, satisfies 1. So does the I plus 1. Okay, so this is what you would want to show in an inductive argument. So the first part, is this easy? So what does the I equals 1 mean? It just means that after one iteration, the biggest element comes to the end. Okay. And why is that? Yeah, so the biggest element just keeps getting swapped. If it was not in the end to start with, you basically, if this is the largest element, it just keeps getting swapped with the rest. So you can easily see that this works. Okay, so I equals 1 is easy. Okay, so what about the inductive step? So then we want to say that this is called the base case, and so for those of you who are rusty on induction, this is base case and this is the inductive step. Okay, so here we want to show, assuming until the ith iteration this property held, you want to show it for I plus 1. Yeah.
So even if we want to formally write I plus 1, how do we formally write this to prove the base case? What statement should we write?
Yeah, so to prove the base case, what you would say is, look at where the largest element was. Okay? And suppose it was in some position. Then in the first iteration, that element will, so you've got to say that in the execution of this loop, it will always get swapped. Okay? And it will therefore be moved to the very end of that. So at that point, it's okay to be that informal. Yeah. So, yeah, that's a good point. Okay. Yeah, and also I emphasize these kind of details more in the beginning of the course. So once you get a hang of proofs, you don't have to write every single detail very carefully. So, yeah.
So for the inductive case,
Yeah.
We can assume that everything after the ith array is not there, and then we again have the base case because now the ith largest is the largest in the.
Okay, so that's almost completely true, right? So what he's, that's almost the full proof. You just have to show that the part that is the largest won't get messed around, which is fine. So does everyone hear what he said? So what he said is, okay, so the inductive step, the inductive assumption, which is that it holds in the ith iteration, means that after I iterations, you have a n I here, then a n I minus 1, and a1, a n1. Remember, I called a n1 the largest, a n2 the second largest, and so on. There's just some indices. Okay. So until so after I iterations, you have an array that looks like this. Okay. And now, what happens in the I plus 1th iteration? Right? So you again go from left to right, doing some swaps. Okay. And by the exact same argument we used for the base case, the I plus 1th smallest element is the guy that's going to be bumped all the way here, okay, to this point. Okay, so the I plus 1 smallest element which we are denoting a n I plus 1 will go into its right position. Okay. And no further, right? And nothing on the left will get swapped with something on the right because those were the I largest elements. Okay. So this is what the ith iteration will do. It might do other swaps, mind you. Right? So it might do other swaps, but this definitely will happen. Okay, so this is what this is, and this is all we are claiming, right? And then this means that I plus 1 smallest onwards are in their right position. And this is what the inductive step is. Okay, so this completes the proof. Because we just established that assuming ith iteration satisfies 1, so does I plus 1. I'll pause a little bit for that.
Should the largest element not the smallest?
Sorry?
I mean, it shows the
largest.
Yeah.
All of these should be largest. Good catch. Thanks. Good, so yeah.
Go back to the previous slide just for a moment.
Yeah. So this is what we want to show by induction. So it's assuming the ith iteration satisfies this observation that he came up with, then so does the I plus 1. And, the proof is actually somewhat simple. You just I'm showing you guys how you very formally write a proof so that it's get used to it. Yeah.
So the proof is to prove the correctness or to prove the algorithm lawless and
Yeah, so as I was observing, so the way I wrote the algorithm, proving that it ends in n steps is, so if the algorithm ends at all, it has to return a sorted list, because I have this while condition that says as long as it's not sorted, keep doing this. Right, so showing that the algorithm terminates is equivalent to showing that it actually sorts the array, because it will it will end only if the array is sorted.
do we need to write down the statement that so the program will end eventually?
Right, so that's what my claim was, that the algorithm always ends in a finite number of steps, and in fact I said it will end after at most n iterations of this while loop.
Can we just write the claim without the proof?
Oh, so this is all the proof, right? What do you mean? Maybe I'm missing something.
It is written before the proof, so do we need to restate the claim after the proof?
Oh, no, it's fine. I mean, you have the claim and then you proved it, right? So that's, maybe I'm missing something when you're asking. So,
the proof is written after the claim.
Yes.
And the claim is to use, the claim is about it will end eventually.
Yes.
But the proof is about the correctness of the program.
Okay, yeah, you can have a line at the very end which says, now we say that, okay, we have shown that it always ends, and if the algorithm ends, then it means that it is sorted, because if it weren't sorted, then it would not have ended, right? So that's, you have to write this argument, yes, I agree. So was there a different question? Saw some hand going up there. Oh, okay.
Could you share some other examples on Canvas of maybe a bit more complicated case of proof?
Yeah, so we'll see one more today, and I will give a link to some notes about how you write, Okay, so this is, so as you're saying, this is more of a caricature example, right? So it's very simple setting. But actually, most of the things we will see won't be very complicated. The correctness will usually be kind of okay. Yeah, when we go to approximations, then you have to do a little bit more work to actually show that it satisfies certain properties. But the early things, the correctness will be somewhat easy. Okay, so I want to do a different example, one where also we try to reason about correctness. Okay, and this will hopefully give you a slightly different feel. It will have a different feel from the one that we just looked at. Okay. So it's so the example is about paths and graphs. Okay, so what is the problem here? So you have a simple undirected graph. So what's a simple graph?
No self.
Yeah, no self loops, no multiple edges. Okay, so that's simple. That's the definition of simple. And it's an undirected graph. Okay. You're given two vertices. Okay, so you have a graph G. There's some vertices, some edges. Okay, so you're given U and V. You want to know if there's a path from U to V.
Yeah.
Okay. So that's the question. And I have this algorithm, right? So let's parse this for a bit. Okay. So I hope there's no bugs in this, but okay. So it's so all I'm saying is you maintain an array, call it explored, and initialize it to false. Okay. So initialize it to false, and there's a procedure which is basically explore of U. It's a recursive procedure, What it does is first it sets the explored bit of that particular u to true. Okay, so u is a vertex. Okay. Sets explored of that to be true. And then you look at every neighbor of u. So in this case, u was that vertex, there's only one neighbor. Okay, so when you are exploring something else, when you are exploring that vertex, maybe now you have 4 neighbors. Okay, so you loop through all the neighbors. Okay, and you recursively run this explore procedure on the neighbor as long as it's not already explored. So if it's explored, it means that this is just an intuitive notion, it means you've already seen all of its neighbors. So how should the graph be stored to do this well? Yeah, list works perfectly for this, right? So it's an adjacency list. Assume that the graph is stored as an adjacency list. Okay. So this is what this is. So for every neighbor, you go through, you run it recursively. Okay. And in the end, you say that if the explored of v is true, then return yes, otherwise return no. Okay? Yes means that there is a path. Right? So the question we want to answer is if there is a path. Okay, so right, so 2 questions. Does this algorithm always correctly find if there's a path or not? And second, how long it takes? So these are the 2 questions we'd like to answer. Okay, so let's look at correctness. So actually I'll give you a couple of minutes to stare at the algorithm for those of you who have not seen. Actually, for those who have seen, what is this algorithm called?
Depth first search.
Yeah, so this is the definition of depth first search. This is something hopefully all of you have seen. Depth first search. Okay, it's called depth first because you start at a node, go to its neighbor, start exploring that, go to its neighbor, and so on. Yes, that's how this algorithm will execute if you execute it on a machine. So it goes deep first and comes back and so on. Alright, so this is depth first search, and I want to say that as long as there's a path, you will actually find it correctly. Okay, so correctness, we have to say, so correctness means, what do we now have to claim? So that's again the statement first. What would be the claim you'd like to show?
There exists a path.
If a path exists. Yeah, so exactly. So if a path exists, you return yes, else you return no. Yes, else we return no. Okay. Now, good. So this is as simple as it gets, right? This is just the correctness claim and the proof. Okay. So how would you prove that? So in some sense, you want to prove 2 things, right? So you want to show that if a path exists, you always return yes. If there is no path, you always return no. Okay. So that's what you show. So we're going to show 2 things. So let's start with the first one. Okay, so let's start with the first one, which is if a path exists, you return yes. Okay, so that's I cannot rewrite. So how would you show that if a path exists, then you always return yes?
We can assume a path exists.
Sorry?
Well, first we can assume a path exists.
Yes, so good. So you assume there is a path from U to V.
Assume the condition.
To V. And let's call some intermediate things, right? Let's give some names. So let's call this U1, U2, and there's multiple edges, so I'm not going to write them, and this is some U. Oh, this is actually very bad, I think, unfortunately. PowerPoint seems to crash and lose all my. Okay, so give me a second. So I'm going to try to see if this can be fixed. If not, actually, someone will have to reconstruct this from the video, I think, because there's no way. I mean, unfortunately, PowerPoint seems to be doing this. It did this once yesterday. It worked fine last year, so I'm going to try to see if there's some fix for this. But now I will lose everything I have written. Just, yeah, I don't know how to fix this. So maybe if this continues from next time, I'll use something other than PowerPoint.
Or you can also use autosave.
Oh, there's an autosave that does this frequently?
Yeah, like you can set the frequency like how.
Oh, okay. So I'm going to start doing this right now. Yeah, sorry guys, this is. So meanwhile, think about the proof. So how would you show the connectedness? So we want to say that if a path exists, okay, so this is the first part of the claim that we want to show. Okay, and we said that the path has some labels, it has U, this is V, and so this we gave them some names, so these are U1 through UK. Okay, so how would you say that this algorithm will always return yes if there exists a path? Yeah, so let me come back. Yeah.
We could construct it from like the end case where the vertices are adjacent, and in that case B is neighbor of UK and it will return yes, and then we go on to show that.
So you're saying if U was equal to UK,
yeah,
then you would have returned yes.
Because it's still the neighbor's less.
Okay, because then you would have actually correct. So you're saying that if U were UK, okay, procedure would have said yes. Okay. Then?
And then like we just keep on doing it for each of the, since we are like running explore on each of the paths, so like we can like backtrace into it. Like,
intuitively, that's what you want to say, but how would you formally say this? Right, so what he's saying is, if at some point in the algorithm, explore of UK was called, okay? Remember that you only call explore of U, right? And what we are saying is, if at some point in the algorithm, explore of UK was called, then the answer would be yes. Okay? So now what he has reduced the problem to is showing that explore of UK was called at some point. And what he also said is that you can reduce the calling of explore of UK to calling of explore UK minus 1. Okay. And so on. So what would, so how would you formally say something like this? Yeah.
So if I call a neighbor of UK,
yeah,
then I would get UK.
Exactly. So if you had called, yeah, that's true. If you called any neighbor of UK, you would have gotten this. Yes.
So if I call a neighbor which is on the path, then also it will return.
Correct. Then you will also call explore of UK.
Yeah.
Correct. So right, that's what you want to say, right? Yeah.
I would like to say that if about the length of the path, so if the length of the path is 1, then it is obviously that we can reach B. And so suppose if the path length A
Is some
and we
F.
can reach that, and then we may show that if its length is A plus 1, then all the path is length A, we can reach them. And if there is a path, then there must exist a path from length A to length A plus 1.
Yeah, so this is again almost the same proof. So you are saying that we will prove this by induction on the length of the path from U to V. Path length is 1, then it's trivial. If the path length is L, assume it is true, and you want to show it for L plus 1. Right? But the way you prove it would be exactly the same. So what you would say is, you would say that so that's a perfectly valid proof. Okay, so but I'll probably write the one that somebody else suggested, because that's easier to write down for me since we have only a couple of minutes. Okay. So what we will say is that proof by induction that explore of UI is called. Okay. So UI is called for all I. So for I going from 1 through k. You know that if explore of UK is called, then you're done. Okay, because then V will be reached. Okay. So this is going to be our this is going to be the inductive statement. So we prove by induction that explore of UI is called for all I in 1 through k. So is this point clear? That at some point the function call explore of UI is going to happen. So that will be the inductive claim. And yeah, so that's what you want to show. And now what's the base case for this?
U1 is called.
Yeah, so U1 is called, right? So I equals 1. So we want to say U1 is called at some point. And why is this true?
Because it's a direct neighbor of U.
Yeah, U1 is a direct neighbor of U, and this procedure, you iterate through all the neighbors, you call it. Okay, so this is always called. And I equals 1 is trivially true. Yeah, unfortunately, if I do auto save, then I have to be in the mode where it will actually save. I can't be in a presenter mode. Okay, so that's why I'm doing this. Okay, so this is trivially true. And now you can actually show that the inductive step is also very easy, right? Because you can say that look at the time when ui minus 1 is called. You will say that, okay, let's assume for some I. This means that explore of ui is called. Yeah.
I don't understand the base case.
So do you understand the claim, the inductive claim? So it says that explore of ui is called for all I in 1 through k. Okay? And I equals 1 is like saying explore of u1 is called. Okay? So why is it true that explore of u1 is called? Right? So let's see. Okay, so we know that we are, but I mean, initially you are calling explore of u, correct? So you're calling explore of u. What does it do? It first sets this explored bit of u itself to be true. Then it goes through all the neighbors of u, okay, and it explores each of them in some order. And in the process, you could be exploring other stuff and so on. It doesn't matter. Okay, but in particular, u1, which was a neighbor of u, would be, would show up in this list of neighbors, right? So you will actually call explore of U1. Okay, so this statement, maybe it's not trivial, but it follows from this line of the algorithm. Okay, so let's call this star, and in step star, we consider U1. Okay, so this is why you will call, this is why the base case holds. That U1 is always considered and you will explore that. And now we are saying, let's assume that explore of UI is called. Assume explore of UI is called. I want to show that explore of UI plus 1 is called. How do I show it? Yeah, so when you are in the function call explore of UI, UI plus 1 is one of the neighbors of UI. Therefore, in the same star step, then again, in that call, the step star considers UI plus 1. There's a little bit of twist to it. It considers UI plus 1, but you do some check, right? Sometimes you don't run explore. And why is that not a problem?
Because you only don't run it if it's already been run.
Yeah, so the only time you change that explored bit is when you actually run explore. So that's what you're using now to show that this works. This is just to complete the formula. Okay, and if it was not already run, then you will explore. Okay, so this was the proof. So since we're out of time, I'll probably stop here, think about it for a little bit. And, if someone has been taking notes and they can share with it, it would be great, given that I've lost all the stuff I've written on my slides. Okay, so yeah, this is just an open call.